Hello everyone. So, let us continue our discussion on strain analysis. This is week 5 and our 4th lecture. Today our main topic is strain compatibility. Now, before we go into further details of strain compatibility, let us quickly review the mathematical model for strain that we earlier developed. So, we have epsilon xx, which if you recall differential of ux with respect to x. Similarly, we can also express the same strain along y and along z. So, these are the normal strains, right, and we also have shear strain. So, gamma xy is equal to uy differentiated with respect to x plus ux differentiated with respect to y, and we have two more components, gamma yz and gamma xz. So, yz is again uz differentiated with respect to y plus uy differentiated with respect to z. And the last one, here we have uz differentiated with respect to x plus ux differentiated with respect to z. Now, earlier I gave you a hint that if we have displacement field how it is defined? We have three components ux, uy and uz, right. Once we know the displacement field, which are functions of x, y, z, then we can easily find out what are the different strain components. So, this is equation 1, equation 2, equation 3, and then we have shear stresses equation 4, 5 and shear strains. Now, the forward problem is very easy. We define the displacement field in terms of ux, uy, uz, and then we differentiate these with respect to x, y, z, and appropriately we evaluate different strain components. Now, the problem comes when we start from the strain and wish to find out what are our displacement fields. For example, if you have a say beam and then we apply some load and we measure some strain, say this location, this location, this location. So, these are the locations and we wish to find out how this beam is going to deform by measuring this strain, because we can measure strain. Also, we can measure displacement, but if we wish to figure out from strain what is the displacement component, then we have trouble. The reason is we can evaluate ux from this first equation. At the same time, we have equation 4 and equation 6, there also we have this ux embedded. Now, the question is, out of all these possibilities, which one is correct and how should we ensure that our estimation of displacement from the strain is actually correct? And for that we have this strain compatibility condition. What does it mean in simple words? You can easily see that ux, uy, uz are there in normal strain as well as in shear strain, and therefore, intuitively we can expect that there will be some interrelation between say epsilon xx, yy and say gamma xy. Similarly, there may be some other relations among these strain components, because they originate from this displacement field ux, uy, uz. That is what we are going to investigate, and for that let us first consider equation 1. So, that means this one, which is epsilon xx is equal to ux differentiated with respect to x. Now, what we do if we differentiate epsilon xx twice with respect to y, so what we have, we can rewrite this equation. So, we will differentiate this twice with respect to y, and then if we write this expression, what we have say this equation is. Similarly, we can consider the second equation. What we have in second equation, epsilon yy is equal to uy differentiated with respect to y. And this equation, if we differentiate twice with respect to x, then obviously we have this equation. So, this is number 8. Now, if we add these two equations, so 7 plus 8, what we get? Right. Now, this third bracketed quantity, you can easily identify this is nothing but gamma xy. So, we get a new relation epsilon xx differentiated twice with respect to y plus epsilon yy differentiated twice with respect to x is equal to gamma xy differentiated with respect to x and y. So, this equation is equation say 9, okay? Or this is the first compatibility equation. So, let us write it here. So, we have the first compatibility equation. So, say this is equation A. So, we considered epsilon xx and epsilon yy here in the first two equations, and then we developed equation 7 and equation 8, right. Now, if you follow the same route and if we take other two, say this one epsilon yy and epsilon zz, we will get another similar equation, and then finally, if we consider epsilon xx and epsilon zz, we will get the third equation, which are very similar. So, let us write down those equations. So, this is second compatibility equation. Third one is so, we have first three compatibility equations derived, right. Now, if you look at these expressions, what we have in these equations is, if you see the first equation, epsilon xx yy and gamma xy, right. And as I told you at the beginning, if you look at the forward problem, that means if we start from the displacement field ux, uy, uz, then obviously the problem is straightforward. We need to differentiate those components with respect to x, y, z appropriately, and then we can find out all these strain components. Now, obviously, as I explained, look at this expression. If we consider epsilon xx, epsilon yy and gamma xy, we can develop a interrelation between them, and that is what we have here, and that is how we have developed these three equations. If I follow the same logic, what I see for the shear strains, again if you look at gamma xy, it has ux, ey differentiated appropriately with respect to x and y. Similarly, in other components also we have the same displacement field appearing. That means, again, before deriving anything, we can expect that there is interrelation between these shear strain, and let us investigate that. So, what we have here is, say, the fourth equation here, that is the first shear strain is gamma xy. So, we have this expression, right. And then what we do, we differentiate this gamma xy with respect to z. Obviously, it will also appear here, right. Okay. Then let us consider gamma yz. The expression is this one. Now, we differentiate this quantity with respect to x. So, on both sides we differentiate with respect to x. So, this is our, say, if I follow the number, 7th equation, 8th equation, and then the last one we have gamma xz, which is equal to and this quantity we differentiate with respect to y. This equation is the 9th equation. Now, what we do, we add these two, and from that quantity we subtract this one. So, this is the operation let us do. So, what we have? We have right. Okay. Now, if we do that, see what happens on the right hand side. So, what we have, let me write down the quantity first. So, we have this quantity. Okay. Now, carefully identify. So, this gets cancelled and also this one gets cancelled, right. So, effectively what we have twice of this quantity and then we can remove all this. Okay. Now, what we do, this expression, if we differentiate both sides with respect to z, we have 2 times this quantity, right. Now, if you look at this right hand side, we can actually simplify this and we can rewrite this expression. So, we have 2 times right, and we can identify this quantity is nothing but epsilon z z. So, if I rewrite this equation, what we get is so what we have here another equation . So, this is say equation D, and similarly we can develop 2 more equations. Now, here we differentiated with respect to z, and I mean if we add other 2 equations and subtract the third one and then follow the same mathematical operation, we can develop 2 more equations which are so this is equation E, and the last one so that is the 6th equation. So, altogether these 6 equations are the strain compatibility equations. Now, you see we have the forward problem again. If we start from the displacement field, then forward problem is the strain components that we can easily evaluate. Okay. But all 6 strain components we can correlate with each other, and what effectively we get these 6 conditions that actually interrelates all different strain components. So, these are called Saint-Venant's strain compatibility conditions. Right. Now, once we derive this strain compatibility condition, now we can uniquely solve ux, uy and uz from the strain. So, we can solve the forward problem. If we start from displacement field, we can easily find out all strain components, and if we know strain components and if we know compatibility conditions, then we can also figure out all the displacement components from the different strain components, because they must satisfy this strain compatibility conditions. Okay. It is very important. We will solve some problem in the next class, but for the time being you go through the derivations, and of course, you repeat yourself for this two equations, and of course, this one also. I have derived this equation and this equation. Repeat the same procedure and you can derive the remaining equations, right. So, try that, and if you have any trouble, do let us know. Otherwise, these are the strain compatibility conditions. Fine. Okay. So, now just one more thing is that we have again the forward problem is that from the displacement field we can easily find out the strain components, right. So, say these are the different 6 strain components. Okay. So, if I consider that in a matrix form, we have this one. Again, this is a symmetric matrix, right. So, for any problem, if we know the displacement field, we can actually find out this strains and we can formulate the 3D problem. But in some cases, again we can reduce the problem size. For example, if we have, very often we encounter this type of structure, say a dam. So, we have a dam and on this side we have water, right. Now, this is a schematic diagram of the dam. Normally, this type of structure, their lateral extent, this dimension is much larger compared to other dimensions, say this one or this one, right. Even the base, okay. If we consider the base, obviously, this length of this dam is really bigger compared to all other dimensions. Now, for this problem, just imagine if we wish to evaluate the elongation along this direction and say that is delta L, and the strain obviously along this direction will be delta L by capital L, right. Now, this denominator is really very high. What does it mean? It means that this strain component is extremely low, right. And in fact, in practical problems, this dimension is too high that this strain really small and we can neglect. Okay. Now, what we mean in terms of the strain component in this matrix is that we can neglect one dimension, say z. Okay. Now, if that is the case, if you recall for stress analysis, we had a similar situation where stresses along the z direction we neglected and we had a problem what we called plane stress problem. Now, in case of strain, if we have similar situation, in one direction, in this case it is the z direction. If we can neglect, that means these three components are practically 0, then we get a special case which is called plane strain, right, plane strain. We have dam structure, then retaining walls. Very often we use retaining walls, a wall that retains a soil mass. So, this is a retaining wall, and on this side we have some soil. So, this side we have soil, and again these type of structures, they have one dimension really large compared to other. So, along this direction the dimension is too large, right. In that case we can model it as a plane strain problem, right. Okay. Now, if that is the case, then what we have? We have epsilon xx, epsilon yy, and then gamma xy. Now, if you recall, epsilon pq of a line having a direction cosines nx, ny, nz, the expression we derived earlier is this one. Now, if these quantities are 0, then obviously we can further modify the expression. So, we can neglect this and we have epsilon pq for 2 dimension is this one, right. And again we have nx is equal to cos alpha and ny is equal to sin alpha, right. This we explained earlier. So, if we adopt that expression for direction cosine, so we have epsilon xx cos square alpha plus epsilon yy sin square alpha plus we can write half gamma xy twice of cos alpha sin alpha. And then if we further use the expression of cos square alpha and sin square alpha in terms of cos 2 alpha, so you can further simplify this expression, right. And then the simplified expression will be epsilon xx plus epsilon yy divided by 2 plus epsilon xx minus epsilon yy by 2 cosine of 2 alpha plus gamma xy sine of 2 alpha, right. Exactly similar expression be derived in case of plane stress problem. Now, we can also derive principal stresses in this case epsilon 1, 2, and the principal stresses again you can derive. So, it will be epsilon xx plus epsilon yy by 2 plus minus square root of epsilon xx minus epsilon yy by 2 whole square plus gamma xy by 2 whole square. In fact, if I borrow the same analogy that we discussed in case of stress analysis, so this is epsilon average plus minus r, where r is the radius of the Mohr circle and that radius is given by epsilon xx minus epsilon yy by 2 whole square plus gamma xy divided by 2 whole square right. So, if we find out the block diagram, it is a 2D problem. We have again epsilon xx, then this is gamma xy, and epsilon yy. And for that again, if you recall, we have Mohr circle. We can easily draw the Mohr circle, epsilon ii and epsilon ij, right. So, if we have say 2 points, then we can draw the Mohr circle, right, and these are the principal strains and maximum shear strain we can find out. So, this is the maximum shear strain. So, maximum shear strain gamma max is nothing but R what we have derived here, right. And as we had in case of stress analysis, with maximum shear stress we will have epsilon, and that epsilon is actually given by the average of these two, right. So, it is epsilon 1 plus epsilon 2 divided by 2, right, and that completes the exercise. Obviously, the Mohr circle we have the lower half, which I am not drawing. And from the figure again, if you recall, the angle between the principal strain and the maximum shear strain is, in the Mohr circle it is 90 degree. In reality, it will be half of that. So, it is 45 degree, right. So, that still holds good, and that is the angle between these two extremes. So, this is a special case, what we call plane strain problem. And in the next class, what we will do, we will solve some more example for 2D and 3D problem, and we will see how we can use these models and ensure compatibility conditions, and as well as we can draw the Mohr circle to find out strain in any arbitrary directions. That will be the discussion for the tomorrow's class. If you have any doubt, please let us know. We will try to clear it. Thank you very much.